Hello guys, we're going to take a look at 7.4, the hypothesis test for one population mean. Okay, so this is another hypothesis test. So you're going to see it's similar to the hypothesis test that we've seen for one proportion, and it's going to look a little bit similar to the confidence intervals that we just did over population means. Okay, so I'll point out some of the similarities in here, but our setup is going to be very much following that same state, plan, do, conclude model that we've used pretty frequently at this point. Okay, so first thing, we are talking about a one sample t-test. Okay, and we're going to be talking about means. Okay, so my parameter, the mu, is the true mean in context. Okay, so not a proportion this time, but a mean. Okay, the hypotheses, those we'll get into a little bit later on, but they are again going to be our null hypothesis, HO, and our alternative hypothesis, HA. And our null is, of course, going to be that the mean is equal to the claim that they presented to us in the problem. Okay. Our statistic is going to be X bar, and that's going to be the sample mean. Okay. So I'll make a little note of it here just so you remember this is our sample mean. And of course, that is our statistic, our estimate that we'll use to build our model from. Okay. Our significance level, still 0.05 unless we get a new number from them in the problem. Stick to that 95% confidence. Okay. Now, when we plan to use this normal model, again, okay, we are a t-test this time, not a z-test, so we will use a different distribution, but the conditions are going to be pretty similar. So I'm going to walk you through these conditions real quick. So we say random, we want a random sample to avoid biases. Independent, we want our sample size to be less than 10% of the population. Right? And the conditions for normality. So here they're marked with t distribution, okay? So I'm going to kind of walk you through the different ways that you can establish normality, okay? So the first one is the easiest one. It could be stated in your problem that this population is normally distributed, and therefore we know that the sample that we take is also normally distributed. Our second option is the central limit theorem. Okay, so CLT requires n to be greater than 30. Okay, so a sample size of at least 30 will guarantee that your distribution is approximately normal, and that takes care of it. Okay, now if you can't do either of those, generally it'll fall into one of those two categories. But if you can't, you can make a dot plot, okay, and check for outliers, okay? And basically you can say that the data looks approximately normal, therefore I'm going to assume that it's normal. And your fourth and final option is to just assume normality, okay? Majority of the time, guys, we are going to have data that is normally distributed because otherwise, what are we really trying to understand from this information, right? So if you can't find a statement about it being normal, if you can't use the central limit theorem, and you don't have enough information to make a good dot plot, you can just assume normality at that point. Okay, so that is kind of the planning stage of the one sample t-test, right? We've stated the key parameters and statistics, and then we've gone through our conditions to make sure that this is valid for testing. Okay, so then we are ready to move into the computation phase, right? The do phase. So when we do this test, our test statistic is calculated very similar to the Z statistic that we've done previously, but this time it's T star instead of Z star, okay? And you're going to see it looks very similar, X bar minus mu over SX over square root n, right? Stat minus parameter over standard deviation. It's just kind of following the same pattern, slightly different statistics rather than proportions, but it's kind of the same concept. Okay. Um, Following through that, you set it up, write out your specific variables, fill in your numbers, and then make sure you draw that normal distribution with your t distribution to look up the p-value. Okay. So that is our state, plan, do, portion of this test. We'll talk about the conclusion a little bit later on in this section. But first, let's look at hypotheses. Feel free to pause or go back and look at any of these that you were not able to write down. Okay, let's talk about our hypotheses now. Okay, the hypotheses here are going to be, of course, my null hypothesis, which we've seen many times at this point, and my alternative hypothesis. Okay, and the null hypothesis is always going to be an equals value, okay? And we're going to say that it's going to equal the assumed population. Sometimes you hear me call it also a claim, but it is what we are assuming the population to be. Our conclusion relies on us assuming that this is true, right? So if at some point we ran into a study where our null hypothesis was completely wrong, and someone says, hey, by the way, you just picked the wrong number, that throws our entire study out the window. Okay, so remember that that is assumed to be true at the beginning of our conclusion. Okay, now the alternative hypothesis can be set up as less than, greater than, or does not equal, depending on which tails you want to use for your test. And it's basically talking about what we think the value of the population mean should be. Okay, so we have our assumed value, and then we have the question of, well, I think it's greater than, I think it's less than, or I think it's not actually that number. And that's what the test is trying to show, that we have data that matches the null hypothesis or does not match and is more in line with our alternative. Okay, and basically with that, we run into one of two conclusions, which are down here at the bottom. If our sample is matching with our null hypothesis, we have to fail to reject that hypothesis. And if it's contrary to that, right, if we get a value that looks different than that, we will reject the null hypothesis. Okay, so these two conclusions, either failing to reject the null hypothesis or rejecting the null hypothesis, or shortly said as rejecting the hoe. Those are the only two conclusions we reach. Remember, we never accept a hypothesis. We merely have proof that the assumption is incorrect. Okay. And it can always be that our sample was maybe unlucky and just fell on the high end of the distribution or the low end of the distribution and kind of just messed up our results. So because of that, because samples have variability, we only make decisions about either saying we have evidence against the null hypothesis or we don't. So make sure you get all this information down, and then let's move into our conclusions. Now, to reach our conclusions, we are going to use the sample mean as our approximation point for the true population mean, right? So we're going to look at the sample and we're going to say, hey, is this sample very far from our assumed value? And does that tell me that I have enough evidence to say that that assumed value might be wrong? Okay, so we use the sample mean x bar, and we're going to calculate the p-value, the probability that we get that sample while assuming that the null hypothesis is true, right? So this is our assumption right here. So we are looking to see, hey, does this give me evidence against this assumption or not? And we come down to our conclusions. Of course, guys, when your p is greater than 0.05 or the significance level, we can fail to reject that null hypothesis. And if we say that, then what are we saying? We have more than that 5% chance of getting this sample purely by chance if the null hypothesis is true, which is basically not convincing evidence that something different than the null hypothesis could be valid. Okay. And if we get a number less than 0.05 for the p-value, then we're ready to reject the null hypothesis. We have convincing evidence for the alternative that we were measuring against, right? Reminder, if the p-value is low, that means we would get to reject the hoe. Okay. So interpret our p-value. Assuming the null hypothesis is true, there is a p-value, generally 5%, probability of getting the sample mean, x bar, or greater, less, more extreme, purely by chance. Since your p-value is greater than or less than 0.05, we write our conclusion, reject or fail to reject the null hypothesis, and we do or do not have evidence that the true mean is greater than, less than, or more extreme than the null hypothesis. And that last piece is actually should just match up with your alternative hypothesis, which is either greater than, less than, or does not equal. Okay. Make sure that you master this art of writing this conclusion. That's what's going to get you the most points on your EP exam. Pause here and feel free to go back if you missed some information. Let's dive right into a quick example. So in our first example, we have a sample of 25 college students answering how many hours of sleep they got per night on average. And we have that data summarized in that short bracket set there. And the US Sleep Foundation says that adults should get 7 hours of sleep per night. Is the mean amount of sleep that college students get less than the foundation is going to recommend? Well, let's see. Okay, so first thing, let's go ahead and dive into our state section. If you want to pause and try to state the variables yourself, go for it. And here you will see my stated variables and information. So here I let out with the population mean, the true mean amount of sleep that college students get per night. And I took the average of my sample. Okay, so this is, of course, my sample mean. And I just did it with the calculator, and I came up with 6.56 as my mean number of hours that college students sleep in this sample. My significance level is 0.05, which means I will make a 95% confident guess. And my hypotheses, my null hypothesis says that the mean is equal to 7, and my alternative, my claim against this is going to be that the mean amount of sleep that they get is, of course, less than 7. Okay, so that is our first step, to state what we were able to take away from the problem. Okay, now I could do a few other things here and mention some details. I can do things like mention my sample size, which is 25. I could calculate my standard deviation if I wanted to. However, this is kind of the bare bones of what we need to start this problem. Let's dive into our plan section next, okay? So when we plan, remember, we're going to lead out by stating what test we want to use. Go ahead and see how far into the planning section you get before you progress further. Now, as I'm planning here, you'll see that we have a random sample of 25 college students, and we can judge this to be independent because 25 is less than 10% of all college students. However, my criteria for normality is a little more challenging in this case, okay? What conditions do I need in order to be normal for this type of test? So hopefully you guys went and looked back and saw that normality can come from either being stated, which in this problem we are not, okay? We could have a sample size that is greater than 30, which we do not, okay? And we could then go to plot our data and see that there are no outliers. And if we roughly calculated our data and looked at it, we would notice that there are no outliers. That's kind of my check condition for this case. And the worst case scenario was if you cannot get any of those to work, we should go ahead and assume that they are normal so that we can proceed with our test. Okay, so that takes us through the planning portion. Okay, let's dive into the doing of the test. Okay, so I went ahead and stated my test, and now we're ready to perform our calculations. So I went ahead and drew my normal curve, and I'm showing that I care about being on this left side of the curve because I'm asking about a p is less than hypothesis. Okay, so remember our t distribution is going to be n minus 1 degrees of freedom. Okay, so we always go 20 based on our sample size, 25 minus 1 to get that degrees of freedom. okay? And I'm going to calculate my statistic over here, x bar minus mu over sx over square root n, okay? And we find this statistic value, my t value of negative 1.9005. Now, with this, what can we do next? Let's look up the value on our distribution and see what our p-value, our probability is about this. So here you can see I've calculated our p-value, okay? And I'm finding out when my x could be less than 6.56. And when I plug this in, we find a p-value of 0.0347. And what jumps out to me is that number is low. It is less than that 0.05. So what conclusion are we going to reach? We are ready to reject based on this information. So let's dive in a little bit further into our conclusions from here. And here are our conclusions. I also went ahead and included the calculator instructions here for you so that you can look at that information as well. So if you wanted to perform the same test in your calculator, you can use that t-test information there and then follow along with that. Okay, so please note you would have to enter that list of data in order to perform the t-test. So you may find it easier to actually calculate the x bar and use that information instead. Okay, but the conclusion, remember, reads, we lead out by assuming the null hypothesis is true. There is a p-value, 0.0347 probability of getting a sample mean of 6.56 or less. Remember, we're or less because that is our hypothesis. And since the p-value is less than 0.05, we reject the null hypothesis and have evidence that college students get less than 1 hour of sleep at night. And that is your first one sample t-test. Okay. So I'm going to go ahead and pull up the results for the second one. I would really suggest stopping here and trying to complete the second test on your own before looking further at this video, because I will show you the results now. So here are the results for our second example, okay? So we are talking about your store's sales, and we really want to do better this year. So our starting point was $300 per day, and our alternative hypothesis is that we would make more than 300 per day. Okay, so here is my state section, and we want to be using a alpha level of 0.01, a 99% confidence level. And this time we went ahead and calculated the standard error up here as well. Okay, so if we come down into our plan section, we can see that we randomly selected 15 days. That is, of course, less than 10% of the population. And we stated that the daily sales is normal. Okay, be careful because that sample size n equals 15 would not be enough to assume normality. Okay, so we needed them to tell us that. Okay, down below here, we're ready to perform our calculations. We will do this test, x bar minus mu over standard error. Calculate that out. We've got our p-value, whereas x is more than $322. And we calculate it and we get 0.002. Okay. And remember, 0.002 is going to, of course, be less than 0.01. So our conclusion arrives here with this. Assuming that null hypothesis is true, we have a 0.0021 probability of getting a sample mean of 322 or more just by chance. Since the p-value is less than 0.01, we reject the null hypothesis and have convincing evidence that the true mean is greater than 300. Okay, so that is a couple of quick examples of one sample t-tests. Okay, good luck and happy studying.